So last time, if you remember, and even if you don't remember, I said to you that if you have a Lie group G and a tangent vector to it at the unity E, then you can expand it to a vector field. Just apply to this vector all possible left translations. Do you still remember what the left translation is? Multiplication from the left by an element of the group. As soon as you do this, you have tangent vectors at all the points, right? And this is a vector field. I'm repeating all this with my main purpose is that if you don't remember it, and if you have doubts about anything, just ask now, because I will not return to it immediately after. So if you apply all possible left translations to just one vector, you have a vector field which is left invariant, which means that if you make a left translation of the whole manifold, then this vector field is mapped onto itself. Yes, Dale, thank you.
How does the group actually act on the vector? Like, what's the group action?
I think you know, but I will. But thank you for a question. As smooth transformation, in particular diffeomorphism, but any smooth map of one manifold into another manifold, gives rise to maps between tangent spaces, which is called the differential of this map. So left translation takes E into G, I mean lambda G, and in particular it maps TEG into TGG. Sounds strange. TGG. You understand? So if you have if you apply all these differentials of all possible left translations to this one vector, you will get one vector at every point. Okay? Just to add to it that if you prefer, by this or that reason, to have right translations, then you can repeat everything, replacing everywhere the word left by the word right. You can get a right invariant vector field. It's not the same. By applying right translations, you understand that there are two translations from E to G, lambda G and rho G, left and right, and they actually are different. Their differentials are not the same. But so we have left invariant vector field, right invariant vector field. This is what I said last time. Now, usually when I teach this or that course, I discover that my students know analysis better than I, so probably now it's also the case. Do you understand the following thing? It is from analysis, it is also called, it was called in my time, the theorem of the existence and uniqueness and existence of solution of ordinary differential equation. You have a manifold, or domain in Euclidean space, and you have a vector field. Let me consider the case when it is nowhere zero. Take one point, it is not zero at this point, which I choose. Then there exists a trajectory. There is a very much unique curve. It is local theorem, so it exists locally around this point. There exists a unique curve. You can call it trajectory or integral curve or whatever you wish. A unique curve which passes through this point, and the velocity vectors at every, this curve is parameterized. Velocity vectors at every point belong to our vector field. And it's unique. Take different point, then take different trajectory. This is, I prefer to say, even if it is not precisely true, the theorem is taught in the standard course of calculus, or I don't know what. I don't know how much it is so. So do you grant me a kind permission to consider this theorem as known? It has very much standard proof in analysis, using Euler polygonal lines and your favorite Arcelli-Ascola lemma, but I prefer just to consider it as known. Do you have your permission, Jared, to consider the theorem as known? So if you have vector field, then you have, it is very much a local theorem. But in many important cases, including the case where I am going to use it, it can be globalized. So, first, a very strange definition. Very strange definition. No.
And microphone.
Hmm?
And the mic.
Microphone, yes, but I don't have chalk.
In that box.
Hmm? This?
Yep.
You sure?
Allowed.
Thank you. And microphone also. Yes. Thank you. So, there is a thing which is called a one-parameter subgroup. Again, G is a Lie group. A one-parameter subgroup. It is very much one parameter, but not so much group. Is a homomorphism. A homomorphism, say gamma, of R into G. I can denote as G sub T gamma of T. So G sub 0 is certainly E because it is homomorphism. Now, certainly its image is a subgroup. And let us discuss very briefly, because it is more or less obvious, what kind of subgroup it can be. It is really continuous, a smooth homomorphism. So first of all, homomorphisms have kernels, right? They have images, so there is an image. Consisting of all GTs, and this is a subgroup in the algebraic sense. But also it has kernel. The kernel of a continuous homomorphism, continuous map, is closed. So what can it be? I state that there are three possibilities. First, that is 0. So topologically, in the set theoretical sense, it is one-to-one. It is R. Then actually the whole line R is mapped into onto one point E. And also it is only one possibility. There is some positive number lambda, and this is lambda z. It is not a very simple algebraic theorem. If it is not 0 and not R, still a closed subset, then there must be the also it doesn't, if it is not 0, then it doesn't contain some neighborhood of 0 or 0, so that in this case it cannot contain numbers, real numbers, arbitrarily close to 0, because if it is Lie homomorphism, so if the velocity vector at 0 is not 0, then certainly it doesn't map. It is one-to-one on some neighborhood of 0. So there exists the smallest positive lambda, which belongs to the kernel, and then it is lambda z. The image GT in these two cases, either it is R, or it is 0, or the intermediate case, then actually this is a circle. Such a periodic map. Okay, with that. And one more important thing, that if it is R, it's not necessarily closed. The canonical example of this situation is the case, so this is not necessarily closed. Closed in the topological sense, not closed test. And the example when it is not closed, the canonical example, is the following. G is a torus. Now there exists a natural projection, actually covering, of by the plane of the torus. You take the plane and you take then a straight, so this is say 0, you take some straight line in the plane and it's image of the torus. And if the slope is irrational, then this curve on the torus will be not close, actually dense in the torus. It's clear. It is clear, right? So when I say one parameter subgroup, it is very much, it is one parameter, yes, but it is subgroup not in in very clear sense, because first of all, it may be not closed. Second of all, you know, it is parameterized, a parameterized curve. If you do not change the curve, in particular do not change the image, but just stretch or compress the parameter, then it will begin a homomorphism of R into G. But the subgroup will be the same. But we consider these two maps as different one-parameter subgroups. This is all about the definitions. Her question, Chris? No? Who? You have a question? You? Then you, please. No. So it's okay. Now theorem. You will like it. For every xi tangent vector G, there exists a unique one-parameter subgroup say that the velocity vector of 0 at 0 is xi. So you understand, this is the tangent element, this is the tangent vector. Then there exists a unique one-parameter subgroup with this velocity vector at 0. And this gives us certainly one-to-one bijection between one-parameter subgroups and elements of T, E, xi. This is the statement. The proof is, again, unfairly simple for such a deep theorem. But do you have the statement? So if xi is 0, this is very much a happy case, then this one-parameter subgroup collapses to one point. What happens if you just multiply this vector by a number? What do you think of lambda? Suppose that this theorem is correct, and is correct. What do you think of this thing? You take gamma, but not with the vector xi, but rather with lambda xi, but only some number. What do you think about that? how much is it the same subgroup or different? It is, yes. Yeah, yes and no. It is the same subgroup or different parameter. Namely, if you apply this to T, then this is gamma xi of lambda T. And this is follows from the theorem, because both are one-parameter subgroups. If this is one-parameter subgroup, this is also a one-parameter subgroup. And the velocity vector here is lambda xi. Now, if you don't want to say anything else, let me prove this theorem. How to prove it? How to prove such a theorem? How to prove the theorem? Any idea? So we have just one vector, not too much. How to produce a one-parameter group from it? First of all, one vector certainly is something which can be used for any construction. Vector field is better, right? But we know how to make a vector field from a vector. So we take xi, take xi, and take L xi. This is the left invariant vector field with L xi of E equal to xi. This is better, because now I have a vector field, vectors at all points. This is xi, but also vectors at all other points, right? And then I can apply that theorem, which we decided to consider as known, and I get at least a curve. So what precisely do I get? I get a curve gamma defined some interval, maybe very small. Epsilon prime and two positive numbers. This is gamma, very short. And it is tangent to my tangent in a very strong sense. So actually vectors from the vector field are the velocity vectors from this is a parameterized curve to gamma. Tangent to L xi, excuse me. Okay? But there is some, it is not what we want, because first we don't know that it is a subgroup, but moreover it is defined only locally. What to do? Take some point here. I probably need to do a new picture. So this is 0, E, gamma of negative epsilon prime, gamma of epsilon here. I take some gamma of t. I can denote it temporarily as g, where t is, say, between 0 and epsilon. I can take t here. And then I apply the transformation lambda g. Left translation by means of g. Now what happens? What happens to the vector field? There is the answer, nothing. It's left invariant, right? Also, I apply this to this curve. And my new curve, I draw it here, but my drawing certainly is not correct precisely. The image of this curve will be tangent to the same vector field, right? the same velocity vectors. And at this point, we can apply the uniqueness theorem. And actually, and we can see that these two curves match where they are both defined, right? So when we shift this to this position, then actually the two curves will match. In what sense? The new curve will be will have slightly different parameter, because parameter 0 now will be here. So parameter will be shifted by t. But otherwise, where both are defined, they match. So we have one curve. And this we can do infinitely in both directions, right? Do this infinitely in both directions. And we get a smooth map, gamma R in G, which is an integral curve of my vector field. Not too much, but still. This curve gamma is left invariant because it is tangent to a left invariant vector field, right? Yes?
Maybe this is obvious. How do you know the image of gamma isn't closed? Or isn't a simple closed group?
I don't know this. I know nothing. I just write gamma R into G. Where do you see any statement that?
Nowhere.
No, you don't see it because it is not here. It may be very much closed. So we have this. We have this map. And it is left invariant. Left invariance, it is left invariant whether it is a circle or whatever. A left invariant map. Left invariant in one sense. That if you, this is E, if you make a left translation using a point on this curve, then this curve is mapped into itself. Do you have the statement? So we choose any point on the, we have this curve, we already have it. Choose any point on it, gamma of t. And we get a new curve. And the statement that it is not a new curve. It's the same curve, but with different parameter. How much different? I write it. So. I take this curve. This is gamma of t. Then I take gamma of u, for some u, and I apply the transformation lambda sub gamma of t to gamma of u, right? And what I get, and this is actually gamma of t times gamma of u. And what I get, the same curve, the same gamma, only the parameter will be t plus u. This gives you a proof that gamma is a group homomorphism. The image is a subgroup. Certainly I also need to check it for the inverse elements, but the check is the same. So gamma of t plus u is gamma of t times gamma of u. This is what in the group. The group is not commutative, but the subgroup is commutative, because t plus u, if you don't know, is equal to u plus t. So I have this construction of the one parameter subgroup lambda xc, and all one parameter subgroups can be obtained by this construction, because every one parameter subgroup, which you only can imagine, have some value of velocity vector at 0, and it is c. then gamma is equal to gamma xi. Because of the uniqueness statement in this in the main theorem about vector fields. So we have this beautiful one-to-one correspondence between one parameter subgroups and vectors in TEG. Questions at this moment? Questions? George, you have many questions maybe now. Not now, I see. Then later on, yes. Now, certainly this theorem about vector fields and trajectories actually has a very long statement with different A, B, and C, and then I don't know how far we need to go along this alphabet. But one of the statements says that if you continuously change the vector field, the trajectories continuously, I mean with all derivatives, then the trajectory will also be changed continuously. So actually we have this curve gamma xi, and if we move xi, then this curve gamma xi is also deformed continuously in very clear sense. You can set this for a particular value gamma xi of t for any chosen xi. Okay? As soon as this is said, I get a very important thing, which is called the exponential map. Which is denoted certainly by as exp. And it is a map of Txc into G. And this map is defined by the formula exponent Tx into G exp xi is equal to gamma xi of 1. So yes, we take xi, we take the one parameter subgroup, and we take the image. This is called the exponential map. Before I answer the question, why this term, probably some of you know this, I must say that this map topologically, how to assign a grade to it, not very bad. At least it is a local diffeomorphism. At some neighborhood of 0 is mapped onto diffeomorphically onto the neighborhood of E. So this is, I prefer to draw them separately. This is TEG, very much Euclidean space. In my, because since I have a two-dimensional blackboard, it is two-dimensional, but it may be not necessarily two-dimensional. And it is mapped into G, like this. And this is some neighborhood of 0, we have a diffeomorphism. This is again an analysis theorem, which is maybe more common than the theorem of existence of solution of ordinary differential equations. This may be smooth. This is I more or less said before. And it has differential at this point. And the differential is the identity. It maps this identity at, differential is 0. It maps this tangent vector into the velocity vector of this curve, right? So precisely the same vector. Identity, if you don't know, is a non-degenerate map. So differential is not degenerate, which means that this map is locally invertible. It's called, how it is called? Inversion theorem, theorem of inverse function. I don't remember. I remember the name, theorem of implicit function theorem. And this is rather inverse function theorem. So if you have a map of a domain in a space of some dimension into the space of the same dimension, and the Jacobian matrix at some point is non-degenerate, but here it is identity, it's not degenerate, then yes, then locally it's invertible. How about this theorem? It belongs to classical analysis.
I think it is the inverse.
Huh?
I think it is the inverse function theorem.
Inverse function theorem. Implicit function theorem is a more general theorem which actually implies inverse function theorem. So however it's called, it is normally assumed to be true. So this is locally a diffeomorphism. Now, certainly there are exercises in my set, but I'm not sure that you got familiar with them. What do you think? If I ask whether it is a global diffeomorphism, probably you would laugh at me. You say that G is not diffeomorphic to Rn, so how to a data space, how can it be diffeomorphism? But it is onto. This is a cherished problem in all textbooks in Lie groups, that if the group G is, I already said this to you, that when people say, let us consider some example of a Lie group. Let us take SL2R. People always take SL2R. So if we take SL2R, it is not onto. If we take SL2C, it is onto. If you have questions, maybe it reminds you of something. If you have questions about this map, my statements, which I guarantee to be correct. My statement is that it is a local diffeomorphism, which maps straight lines through 0 into G onto one-parameter subgroups in G. And actually, the image is the union of all one-parameter subgroups in G. Hope you have some idea of elementary differential geometry, geodesics. Then you could ask, because the short exponential map is also used in Riemannian geometry in the same sense. You take straight lines and map them onto geodesics. And this actually creates some possibility. You want to say that maybe there is some Riemannian structure on G and these are geodesics. Not quite. Not quite, because, as usual, yes and no. And no, because it is not true. Yes, because it is a pseudo-Riemannian manifold. There exists a very canonical pseudo-Riemannian magic in G for which these are geodesics. Nobody has cancelled, as far as I know. The classical Hopf actually every 2 points, at least for this in this case, can be no. Excuse me. Every 2 points can be connected by a geodesic, and here I say that know that one-parameter subgroups of, say, GL2R do not cover R, and this is because this metric actually, forget about it. Say this as a no why, because you probably have this. Now, why exponential? Why do not call it some other way? The answer is very simple. I call it exponential because it is for no other reasons. Let me consider at least now I cannot do anything else. but still I will do this. Let's consider now the example of no. What to do with this? I will probably need to. So we have GL and R. And in the case of GL and R, we really have some one-parameter subgroups which can be easily described. Namely, consider a matrix A. No, I do not say that it is non-degenerate, just a matrix. Now, for matrices, we can consider this thing, e to the power exponential of TA. What is an exponential of B, where if B is some matrix? It is what you can guess. The usual series for the exponential. It is convergent for every matrix B. The proof is the same as classical analysis. Very much convergent series. And this is also a matrix, right? Very easy to compute in examples. E to the power 0 is I. Now, have you ever seen this thing? If you take the most cherished exponential equation, e to the power, the answer to 99% of my questions are yes and no. You say no, this is right, but yes is also right. So this equality, e to the power b plus c equals e to the power b plus e to the power c holds if b and c commute. The usual, this equality can be proved in terms of series and well-known relations between factorials, between, I don't know, binomial coefficients. So this is true if, in analysis. But the proof certainly requires that B and C commutes. It is very easy if you just multiply this series and this series and take the quadratic term. You will see this is not the same as here. Here it will be b plus c squared, well, divided by 2, but I don't care. And here will be something different. And a plus b squared is what? Is a squared plus ab plus ba plus b squared. And here it will be b plus c. Here it will be something different. But in the case when we really need this, we have this equality because T, A, and UA commute, right? So we have this equality, and this means that actually we have this map, which is a one-parameter subgroup of GL and R, right? As soon as we have this, we understand, first of all, the velocity vector of this one subgroup at 0. Velocity vectors belong to the tangent space. Velocity vectors well, this is not a big deal. GL and R is an open set in the Euclidean space of matrices. And for such a manifold as open set in Euclidean space, the tangent space is this Euclidean space. Which means that we have this, and it is very obvious that if we consider this, I can denote this subgroup of this, that is x a of t is e to the power t a, then obviously the velocity vector at 0 is a. That follows immediately from that formula you see a, the coefficient t, so it is obvious. So actually we have how to say a full set of one-parameter subgroups. One-parameter subgroups are determined by their velocity vectors at 0, and for every velocity vector at 0 we have this, which means in particular that the exponential map is truly exponential. It takes the matrix A into e to the power into this into e to the power e to the power A. I have to take this one-parameter subgroup and take t equal to 1. What can be more exponential than this? So at least for the group of matrices, GLN R, for the most important, maybe, Lie group, this exponential mapping is exponential. This is the reason why it's called, at least one of the reasons, why it is called exponential. But now let me say, it is very obvious. Certainly I can draw a diagram on the board, but it will not convince you more than the same statement without a diagram. This exponential map is very much natural. Well, I will draw a diagram, if you insist. You have two Lie groups, G and H. And the homomorphism, say, of H into G, a Lie homomorphism. Then we have also the following. We have T, E, H, DF, DEF, T, E, G, H, G, here this diagram is commutative. I cannot say anything about this. It is obvious. Lie homomorphisms take one-parameter subgroups into one-parameter subgroups. It is obvious. So we have everything here is immediately clear. For example, if you take a subgroup of G, then the tangent space TH will be a subspace of TG. And the exponential map will be the same, just the restriction of the exponential map for G, right? So if your Lie group is a subgroup of the matrix group, and this is so for all our examples, without any exclusion. If our Lie group is a subgroup of GLN R, then actually the same formula, exponential, e to the power A, will give you the exponential map. Now you probably want to ask one question. Please do it. I say if a Lie group is a subgroup of GLN R, if, how much this is this if? If you take an arbitrary Lie group, do you think that it should be Lie isomorphic to a subgroup of a group of matrices. What do you think about this?
Yes.
Yes is better than no. But no is right. There are examples. You know, when you make not only Lie theory, when you make some very natural statement, then somebody nasty immediately gives you a counterexample, and you are upset very much. For example, you say that it's very obvious that a continuous function has derivatives almost everywhere. And then a nasty mathematician, Karl Weierstrass, comes with an example of a function, very much continuous function, the interval 0, 1, which doesn't have derivative at any point. Here also, there is an example of a Lie group which can be embedded into GL and R. And the best example I know, I can give it to you. Maybe you will not be fully satisfied because it requires some tiny knowledge of topology. If you take your favorite example, I mean GL to R, it is very much not simply connected. And if you take its universal cover, a very strange group, then it is possible to prove that it cannot be embedded in any group of matrices. But who cares? Locally it can be embedded. For locally it is always true that any Lie group can be realized as a subgroup of GL and R. So actually this exponential formula holds always. My time is almost over, so I just make some announcement for the next time. Last theory which remains before I pronounce the word Lie algebra is the so-called Cartan theorem that every closed, in topological sense, subgroup of a Lie group is a Lie subgroup. Just imagine you have a Lie group. You have some closed subset which is a subgroup algebraically. It seems that there is a possibility that it's very nasty topologically. But actually, it is not possible. Certainly, if you take R and take Q in R, it is not a Lie subgroup, but Q is not closed, if you don't know. If it is closed, it is a Lie subgroup. And it's very important, because sometimes we need to construct a Lie group. And we just construct a closed subgroup of some other Lie group. In remaining minute and a half, do you have an idea how to prove the theorem? You have G. G is very much a Lie group. Everything is okay with this. And then you take H, a subgroup. What do you need to prove? Just one thing. This is a submanifold. It's closed, it is given. But it is a subgroup, it is given. Also, it should be a submanifold. That's all. It is very much sufficient that if you prove that it is submanifold at one point, at the point E. E belongs to H, and the intersection, and we need to prove that in some neighborhood of E, the intersection of H with this neighborhood E is a submanifold of this neighborhood, because then we can apply left translations and have this for every point. It is not a big deal. So we need to have this at one point. You know, submanifolds have tangent vectors. And the proof consists, we need to get some understanding what a tangent vector to a subgroup can be. Actually, to a subset. Virtual tangent vector. We take a neighborhood of E. We take this set. Exponential map establishes the diffeomorphism of this with a neighborhood of 0 in a linear space in TEG. And then we simply take this vector, make it unit, and call it, no, not call this. And then we take any sequence which converges to 0. And if you have sequence of unique unit vectors, it has a convergent subsequence, and the limit I will call the tangent vector to H. It is all, because then I will consider for this tangent vector to H one-parameter subgroups. I will prove very easily using closedness that this one-parameter subgroup belongs to H, after which I will have some submanifold and all which is spanned by these tangent vectors, and all I will need to do is to prove that H doesn't contain, at least locally at 0, any other points. So the proof is not hard, but today I don't have time for it. So see you Monday.